Hello and welcome to Doc Clay's Chemistry Lessons. Today we're going to be looking at calculating the pH of particular mixing acids and bases. By the end of this lesson then, you should be able to do the following two things. You should be able to calculate the pH of a reaction between a strong acid and a strong base, and you should also be able to calculate the pH of a reaction between a weak acid and a strong base. First of all then, let's look at the reaction between a strong acid and a strong base. And as we're doing these calculations, we've just got in the top right hand corner of our screen our key reaction or calculation equations that we've seen so far, and we'll be using those throughout these equations. We're not necessarily going to use each one in each example. We're also going to look at our methods, and we've boxed them off into three different sets. First of all, and this is common to pretty much all of our mixing reactions, we do our top box here. So if we're mixing a strong acid and a strong base, the first thing that we do is we calculate the moles of H+. Then the second step is to calculate the moles of OH-. Thirdly, we work out if H+ or OH- are in excess. In other words, we work out which number is bigger. If we have H+ in excess, then we come down to this box over on that left-hand side. I'm just going to give this box a number 1. And if the H+ is in excess, then we calculate the excess concentration of H+, and then finally we calculate the pH. Or our other option here is if the OH- is in excess, well then we calculate the concentration of the excess OH-. Then we use our Kw equation that we met before to calculate the H+ ion concentration, and then finally we calculate the pH. So with these steps in mind, let's have a look at some examples. Here we go then, let's look at our example number 1, where we say calculate the pH of a solution formed when 50 cm³ of 0.1 mole per decimeter cubed H2SO4. Note that this is diprotic. If you want to remember how to do diprotic, look at this video now. And what happens if this is added to 25 cm³ of 0.15 mole Dm- of sodium hydroxide. So the first thing to do in step 1 is to calculate the moles of H+. So the mole of H+ we calculate to be 50 times 0.1 over 1,000. And because we got H2SO4, this is actually 2 times 50 times 0.1 over 1,000, which gives us 0.0100 moles of H+. Step 2 then is to work out the moles of OH- that we've added, and we look at our equation here, and this time we got 25 multiplied by 0.1 over 1,000, which gives us 0.00375 mole. We now compare these two values, and we notice that the moles of H+ is in excess. Therefore, we say we've got excess moles of H+, and we determine that to be equal to 0.0100 minus 0.00375, giving us 0.00625 mole of H+ in excess. Because we've now got the excess hydrogen ions, we now simply calculate our excess H+ concentration. So our step 4 is our excess concentration of H+ is equal to the moles of H+ divided by the total volume. And we just have to make sure we're careful here that we used the total volume, which is going to be 50 plus 75, and that is multiplied by 1,000, and that gives us 0.0833 moles per decimeter cubed. And the final step then is just simply to work out the pH, which is equal to minus the log of 0.0833 using our equation for pH equals minus log, and we put that into our calculator and we get 1.08 to 2 decimal places. This time then we're going to look at a different calculation. We're going to calculate the pH of a solution formed when 25 cm cubed of 0.25 mole dm cubed of H2SO4, again a diprotic acid, is added to 100 cm cubed of 0.2 mole dm-3 of sodium hydroxide. So again, the step 1 is to work out the moles of the acid H+, and that again, because it's diprotic, is 25 times by the concentration, so volume times concentration over 1,000. But importantly, once again, we've got to multiply this all by 2 because we got a diprotic acid giving us 0.0125 mole. Then the next step here is to do the mole of OH minus, and again we've got 100 times by 0.2, so that's the volume times the concentration over 1,000, giving us moles of 0.0200 mole. Step 3 then is to decide what's an excess, and this time we got excess OH minus because the moles of OH minus is larger, and so it's 0.02 minus 0.0125, giving us an excess of 0.0075 mole of the OH minus. So this time we've got a strong base in excess, so we've got to work out the concentration of the OH minus, and we do this again, it's the number of moles times by 1,000 divided by the volume. Now here is our important step, that we're now the total volume, so we are 25 centimeters cubed plus 100 centimeters cubed for the volume, giving us a concentration of OH minus, which is 0.0600 moles per decimeter cubed. Now, because we've got a strong base, we now have to use our Kw expression, which we've got over here, where Kw is equal to H plus times by the OH minus, and we can rearrange that equation for H plus is equal to Kw divided by the concentration of OH minus. So our Kw this time we're going to assume is at room temperature. If you need to look at the Kw, you can follow the link to this video, divided by 0.06, and that gives us a concentration here equal to 1.67 times 10 to the minus 13 for the concentration of the hydrogen ions. The final step then is to say pH is equal to minus log of the hydrogen ion concentration. We've just calculated the hydrogen ion concentration to be 1.67 times 10 to the minus 13, giving us the pH to be 12.78. We give this value at the end here in 2 decimal places for the pH. So we've seen there the 2 different routes of working out the pH for a strong acid and a strong base. Both instances we work out the moles of H plus moles of OH minus, work out what's in excess, and then we go either to work out the concentration of H plus from the excess H plus, or the concentration of OH minus from the OH minus there. So now we're going to move on and look at the reaction between a weak acid and a strong base, which is very similar to the strong acid and strong base, but it's got an important couple of differences when we look at the calculations at the end. So first of all, we're going to be calculating the moles of HA. That's because previously we looked at calculating the moles of a H plus, but this time, because we're a weak acid, we assume that most of the concentration is actually as the acid. So this time we calculate the moles of HA, then we calculate the moles of OH minus, and we work out if HA, that's the acid, or OH minus are in excess. If the OH minus is in excess, we'll see that we do as we did before. We have a strong base in excess, so we calculate the excess OH minus concentration, use Kw to calculate H plus concentration, then calculate pH, which is exactly the same as we saw previously. The slight difference this time is if the weak acid is in excess, then what we have to do is we have to work out the concentration of the hydrogen ions, but we can no longer use the strong acid term and assume all the acid is dissociated into H plus. But we have to use the acid dissociation constant equation that we've seen in a previous lecture. If you want to check up on this, how we did this in a previous lecture, just click the link now. Finally, what you're going to do is we're going to use Ka to find out the H plus and go through and calculate the pH. We're going to go ahead and look at an example now. The only other thing to note is that this is also how we calculate buffer pHs, and we'll be looking at those in a future lesson. So let's go and have a look at an example. Here we go then. So we're going to look at this question here that says calculate the pH of the solution formed when 50 cm cubed of 0.5 mole per decimeter cubed ethanoic acid with a pKa of 4.76 is added to 75 centimeters cubed of 0.2 mole per decimeter cubed sodium hydroxide. The first thing, remember then, is to calculate the moles of acid, which is HA. So the mole of the acid, which in this case is ethanoic acid, is equal to the volume times by the concentration divided by 1,000. So it's 50 times by 0.5 over 1,000, which gives a value of 0.025 mole. The second step then is to calculate the mole of OH minus. Apologies, this should say mole of HA here, which is equal to the volume times concentration, 75, times 0.2 divided by 1,000, and that gives a value of 0.015 mole. The final step here in step 3, like we saw with the strong acid, is to decide which is in excess, and this time we've got excess acid, HA, and the amount of that is 0.025 minus 0.015, which is equal to an excess of acid of 0.010 mole. What this means is we've got excess acid, and what we're going to need to use is the Ka, the acid dissociation constant, to calculate a value for the hydrogen ion concentration. So if we just recall that the Ka, acid dissociation constant, it's up the top here, is the concentration of H plus over A minus over the concentration of the acid. And then we can rearrange here for H plus, and we say that Ka here times by the concentration of the acid divided by the salt of the acid. Now, previously when we looked at strong and weak acids, and we looked at weak acids, we could say that A minus, the salt, was equivalent to H plus. But now, because we've mixed solutions together, H plus concentration is no longer equivalent to the A minus concentration. And therefore, in order to work out the concentration of H plus, we've got to find out a value for A minus. So we're just going to quickly pause and see if we can work out what the value of A minus would be in this reaction. So, if we think about the reaction between the acid HA, which in this case is ethanoic acid, and the strong base OH minus, the sodium hydroxide, those two things are going to react together. We've got 0.025 of the acid, and that completely reacts with all of the OH minus before, and so we consume all of the OH minus. What that means is after the reaction, we have 0.01 mole of acid, which we've already described. There's no OH minus because that's reacted with the acid. And essentially we've formed 0.0150 mole of A minus. And what that importantly means is we can assume that the mole of OH minus is going to be equal to the moles of A minus formed. And what that means is that we can use the moles of OH minus directly in our equation to work out the unknown A minus concentration in our acid dissociation equation. What we're left with now then is the acid dissociation constant, which is rearranged, which we describe as Ka is equal to Ha over A minus. Now, because the volumes in both the HA and the A minus concentrations are equivalent, what we can actually do is we can rewrite this as the moles of HA over the V tot, which is the total volume, divided by the moles of A minus over the total volume. These actually cancel out, and we can end up with an expression where we have the moles of HA over the moles of A minus. And so our H plus concentration can now be reduced to Ka is the moles of HA over the moles of A minus, which we've already calculated. And we've also got to work out our value for Ka because we've been given pKa. So just remember that Ka here is equal to 10 to the minus pKa that we've seen in previous lessons. I can therefore put in my values. Ka is going to be 10 to the minus 4.76 as my value for Ka. And then that's going to be multiplied by the moles of HA, which is 0.010, divided by the moles of OH minus, which is the same as the moles of A minus. That is 0.015. And that gives me a H plus concentration equal to 1.16 times 10 to the minus 5. And the final step then is to go to the pH is equal to minus log of H plus concentration. So that's 1.16 times 10 to the minus 6. And I end up with a pH here which is equal to 4.94. Once again, I give that to 2 decimal places as my final answer. Finally then, we're going to have a quick look here to see what happens when we've got the pH of a solution formed when 30 cm cubed 0.2 mole ethanoic acid with a pK of 4.76 is added to 100 cm cubed of 0.1 mole decimeter cubed sodium hydroxide. In this case, we're going to have an excess of base. So once again, we simply do the moles of HA, which is equal to the volume times by the concentration divided by 1000, and that gives us 0.006 mole of HA. We do the mole of OH minus added, which in this case is 100 times by 0.1 divided by 1000. This is giving us a value of 0.010 mole. And then we're looking here to work out what's in excess, and in step 3 we see we've got excess OH minus, and that's equal to 0.01 minus 0.006, giving us an excess of 0.004 mole of OH minus. Therefore, we've got an excess of OH minus, and we're going to use our idea of work out the concentration of OH minus, which is now the 1000 multiplied by the number of moles, which is 0.04, divided by the total volume, which is going to be 100 plus 30, and that gives us 0.0308 moles per decimeter cubed as my concentration for water, for hydroxide. Again, we use our Kw expression. We rearrange our Kw expression to give us the H plus concentration. Kw here, if we're not given it, we're going to assume it's 1 times 10 to the minus 14 over 0.0308, and that's going to give us 3.25 times 10 to the minus 13 as a concentration of H plus ions, and therefore our pH is going to be equal to minus log of the H plus concentration, which is 3.25 times 10 to the minus 13, which is equal to 2 decimal places once again, 12.49. In this final example then, we're just going to look at half neutralization of a weak acid. So here it says calculate the pH of a solution formed when 100 cm cubed of 0.2 mole DM-3 ethanoic acid with a pK of 4.76 is added to 40 cm cubed of 0.25 mole DM-3. So again, we're just going to go through our mole of HA is equal to 100 multiplied by 0.2 divided by 1000, which gives us a moles of 0.02 of the HA. The mole of OH minus then added is equal to 40, the volume, times by the concentration of 0.25 divided by 1000, which gives us 0.0100 mole. Now, that means at this point we've got excess HA, and the excess acid is going to be equal to the difference between the acid and the base, which is equal to 0.0100 mole. Now, if we look and think about what's happened, the acid HA has reacted, and exactly half of that acid has reacted, and that means the salt, we've also got half the amount of the salt compared to the acid has formed. Once again, all of the hydroxide has been used up, the amount of OH minus being equal to the amount of salt formed. Now, in this unique situation, the concentration of hydrogen ions is equal to Ka multiplied by the concentration of the acid over the salt of the acid. And we've seen before that this expression we can describe as Ka is equal to the moles of Ha over the moles of A minus. Now, the thing to note here is that because we got the same amount of A minus as we do of Ha, that expression, there shouldn't be an equal sign there, it's Ka times by the moles of Ha over the moles of A minus. That expression, because the moles of Ha is equal to the moles of A minus, these actually cancel out. And what we find is that the concentration of H plus is equal to the concentration, is equal to Ka. So we've just seen there that the H plus concentration is equal to Ka, and therefore at this unique situation the pH, which is equal to the minus log of the H plus concentration ions, and since pKa is equal to minus log of Ka, then the pH at half neutralization is equal to the pKa, and therefore the pH of this solution is equal to 4.76. That's all for now. Having completed this lesson, you should now be able to calculate the pH of a reaction between a strong acid and a strong base, and also calculate the pH of a reaction between a weak acid and strong base. I'll see you next time.